Could a single inch of steel survive the deep ocean? But researchers recently found a flaw that changes everything here. At these depths, the ocean exerts massive force on hulls. Spheres distribute stress evenly, preventing the metal from buckling inward. Titanium alloys offer incredible strength without adding too much weight. Even a microscopic dent can cause a catastrophic hull failure. Engineers stress test hulls until they finally snap under pressure. That flaw we mentioned involves how metal molecules actually shift. Modern welds must be stronger than the base metal itself. New materials will soon let us reach the deepest trenches. A single square inch feels the weight of one elephant. Spheres distribute force perfectly across every point of the surface. High-grade titanium resists deformation better than standard heavy steel. But hatches and viewports create gaps in this perfect armor. Custom acrylic seals tighten as the outside water pressure increases. The hull actually shrinks slightly when descending into the dark. Freezing temperatures help the metal maintain its rigid molecular structure. It is not just strength, it is about controlled elastic movement. Engineers add extra thickness to account for every tiny imperfection. Sensors track every microfracture before the next deep mission. Extreme macro close-up of metal surface under immense water weight. A perfect sphere distributes pressure evenly across every single point. Hatches and viewports create stress concentrations that threaten structural integrity. Stronger materials allow thinner hulls without sacrificing vital safety margins. At great depths, the hull physically contracts under massive force. Tiny air bubbles in welds can cause catastrophic structural failure. Engineers use ultrasound to detect microscopic defects before they grow. This hidden precision is why these vessels survive the abyss. Neutral buoyancy keeps the hull from experiencing unnecessary additional strain. Next, we examine how life support systems recycle internal air. Titanium alloys provide the perfect balance of weight and strength. A perfect sphere distributes external pressure evenly across the hull. Any slight imperfection creates a weak point for structural failure. But microscopic cracks can grow rapidly under this intense load. Engineers use laser welding to ensure joints are perfectly smooth. If the hull fails, the implosion happens in milliseconds flat. They test these materials in massive high-pressure water tanks. The hull stays intact because it is essentially one piece. Thicker hulls add weight, which limits how deep we travel. Next, we examine how internal air systems handle these depths. Titanium alloys provide the highest strength-to-weight ratio here. A sphere distributes external pressure equally across every single point. Any tiny imperfection becomes a focal point for structural failure. But why do engineers sometimes prefer cylinders over perfect spheres? Cylinders maximize internal living space while still resisting ocean weight. Surprisingly, the hull actually shrinks slightly under extreme deep pressure. The metal acts like a spring, returning to original form. This constant cycling eventually leads to microscopic fatigue and cracks. Every vessel has a calculated depth where physics wins out. Advanced sensors track hull deformation to prevent any sudden collapse. Extreme macro close-up of metal rivets under immense simulated stress. Perfect spheres distribute weight evenly across every single square inch. Titanium alloys provide incredible strength without adding too much weight. But hatches and viewports create dangerous gaps in the structure. Specialized gaskets reseal tighter as external water pressure increases further. Think of an eggshell resisting force from all sides. Repeated cycles of deep dives cause microscopic stress in metal. Engineers use tapered designs to distribute stress away from openings. Even tiny imperfections can lead to a catastrophic hull collapse. We will examine how sensors detect these invisible structural flaws. Extreme macro close-up of metal surface under immense water weight. A perfect sphere distributes incoming pressure evenly across every point. Stronger alloys ensure the hull stays rigid under heavy loads. But hatches create gaps where the structure can easily fail. Specialized rubber gaskets seal these gaps against the deep ocean. The entire submarine actually shrinks slightly when descending very deep. Elastic hulls spring back once the vessel returns to surface. Internal ribs provide the real support against the crushing weight. Engineers track every dive to predict when metal will fatigue. Knowing these limits keeps the crew safe in the abyss. Extreme macro close-up of metal groaning under immense ocean weight. Perfect spheres distribute external force evenly across every single point. High-grade steel offers density, but titanium provides superior strength. But there is a specific flaw hidden within the welds. Tiny microscopic bubbles in welds can trigger a catastrophic implosion. Actually, a submarine hull shrinks slightly when descending very deep. Hit the subscribe button and press the bell icon to get updates. This elasticity prevents the structure from reaching its breaking point. It is basically a very expensive, high-tech soda can. Next, we explore how internal air pressure balances the hull. Extreme macro close-up of metal rivets under immense water pressure. High-strength steel must balance weight with massive structural integrity. Spheres distribute weight evenly, preventing local points of catastrophic failure. Every opening is a potential point for the ocean entry. Engineers grind joints to within a fraction of a millimeter. Repeated cycles of compression slowly weaken even the strongest alloys. Titanium provides superior strength without the heavy penalty of steel. Submarines actually shrink slightly when they descend into the deep. The hull returns to its original shape upon surfacing safely. Mathematics ensures the vessel withstands the weight of the sea. Water weight increases rapidly as we descend into the abyss. Spheres distribute force evenly across every single square inch surface. Specialized steel alloys provide the necessary rigidity against external forces. Even tiny microscopic cracks can lead to sudden structural failure. Surprisingly, the hull actually shrinks slightly under extreme deep pressure. Engineers design hulls to flex without losing their original shape. Titanium offers incredible strength while keeping the submarine remarkably light. This is why some hulls use thick acrylic viewing ports. Conical shapes ensure that pressure actually seals the window tighter. Mastering these forces allows us to explore the dark unknown. Extreme macro close-up of metal groaning under immense water weight. Spheres distribute external pressure evenly across every single surface point. High-grade titanium alloys prevent the hull from buckling inward, but microscopic surface imperfections could trigger a sudden structural collapse. Engineers polish the hull until it is perfectly smooth today. Internal air pressure helps counteract some of the outside force. The hull actually shrinks slightly as the submarine descends deeper. That surface flaw we mentioned earlier is now perfectly sealed. Temperature shifts at depth require careful material expansion gap planning. The submarine expands back to its original shape upon surfacing. At 3 miles down, the ocean exerts truly terrifying force. A sphere distributes weight evenly, preventing any single point failure. Titanium alloys offer incredible strength without adding excessive heavy weight. But the hatches and viewports remain the most vulnerable points. Remarkably, the entire hull actually shrinks slightly under extreme pressure. Freezing deep-sea temperatures make the metal even more brittle. Engineers keep internal air pressure normal to aid structural balance. Every hull has a crush depth where materials simply snap. We survive by respecting the ocean's massive, unforgiving physical power. The facts remain, and the search for truth continues.